So we are looking at derivatives and derivatives as a function. So given some function, we're trying to find the derivative of that function, which is also representative of a function. And that would give us the value of the slope anywhere on that function, original function. So we saw that there were different notations to denote the derivative.
It's not that bad.
Okay. So we need to find the derivative of y. So recall that the derivative of y, so y prime, this is going to equal the limit as h approaches 0 of this. We're looking at the f of x plus h, so plugging in x plus h wherever we see the x. And so we're going to have 1 minus 1 over x plus h minus our f of x function, or in this case, y. And so if we subtract that function off, I have 1 minus 1 over x all over our h value. So let's distribute that negative to the bracket, inside the bracket, and then let's combine like terms, if possible, which it is. So we have the limit as h approaches 0 of 1 minus 1 over x plus h. But notice when we distribute this -1, we get -1 times 1 is -1, and -1 times this -1 over x, that gives me plus 1 over x, all over h. So notice 1 and -1, those cancel out with one another. And we're gonna, if we plugged in 0 wherever we saw an h in our function, we're gonna get an indeterminate form of 1 over x. I'm not 1 over x, sorry, 0 over 0. I'm writing 1 over x. So 0 over 0. And we can't have that indeterminate form. And so what we can do is we can clear this complex fraction. So let's multiply both the numerator and the denominator by the LCD of the fractions within, which would be x all times x plus h. And so when we distribute this, the fractions are going to go away, which was the whole point of doing that. So we get the limit as h goes to 0. We have this negative here. So x plus h cancels, we're going to be left with -x plus, and when we distribute this x times x plus h to the second fraction in that numerator, the x's cancel and we're left with x plus h. Notice that nothing cancels in our numerator or denominator, so we're just going to leave it as h times x all times x plus h. So once we've done that, notice now that in our numerator, -x plus x cancels, and we're just left with that h term in the numerator. And we have an h factor in the denominator, so those can cancel. And so now when we do direct substitution, we're not going to get that indeterminate form anymore. We'll get 1 over x times x, which is 1 over x squared. This was our derivative function, what we just found. So it told us that we wanted to find dy dx. It has that vertical bar, and then x equals the square root of 3. That's telling me I want to evaluate my derivative when x equals root 3. And so when we do this, dy over dx, evaluating this, the derivative of y, evaluating this at root 3, we get that is equal to do it this way. That's equal to 1/√3 quantity squared, which is equal to 1/3. So what is that representing? If we graphed that function of y, if we looked at x equals √3, we would see that it has a slope there of 1/3. So in this next example, it says find dy over dx. So that's representing finding the derivative of a y with respect to x if y is equal to 9 times x raised to the 3/2 power. So dy dx, this is going to equal, again, the limit as h approaches 0. Now that difference quotient. So let's plug in x plus h wherever we see an x, and we would have 9 parentheses, x plus h, all raised to the 3/2 power, minus our y value, which is 9x to the 3/2, all over h. If we go in here and we plug in 0 for h, we get that indeterminate form. And so we need to go and manipulate this. I think that it's helpful to see, instead of seeing that with a fraction as an exponent, maybe seeing that as a radical, it will clue you in what you should do. And so this right here is the same thing as a limit, right? As h goes to 0 of 9, the 3/2 power, the 2 in the denominator is telling me I'm taking the square root of x plus h quantity cubed minus 9 x to the 3/2. So this is the square root of x quantity cubed all over h. And that exactly, it means exactly the same thing. Still doesn't get rid of our indeterminate form though. And so to get rid of that, we want to multiply by the conjugate. You know, we could, if we wanted to, let's do it just to make some, we could factor that 9 out and pull it in front of our limit, just so we don't have to deal with such huge numbers. So this is the same thing as 9 times the limit as h goes to 0. Square root of x plus h quantity cubed minus the square root of x cubed all over h. Let's multiply this by that fancy one to get rid of this indeterminate form. So square root of x plus h quantity cubed plus the square root of x cubed. So x plus h quantity cubed plus the square root of x cubed. So now, since we're multiplying by the conjugate, we can say, well, that's a difference of square, and just square the first term minus the square of the second term. And that's going to get rid of our radicals in that numerator. So we have 9 times the limit as h goes to 0. So if I, again, square this first term, I'm just going to be left with x plus h quantity cubed minus squaring the second term, because these are a difference of cubes. I'm left with x cubed all over, and I'm not going to distribute anything. So h times in the denominator. So h times the square root of x plus h quantity cubed plus the square root of x cubed. So I need to expand out that x plus h quantity cubed. So I'm going to do some work on the side and then plug it in. So if I'm looking at x plus h quantity cubed, this is saying I'm looking at x plus h all times x plus h times x plus h. So if I distribute x plus h times x plus h, we get back x squared plus, and combining like terms, I would get back plus 2xh plus h squared. And then now I have to multiply that by the other x plus h. So if I distribute this out, I get an x squared times x, that's an x cubed, x squared times h, so plus x squared h, plus distributing my 2xh to each term. So 2xh times x, so that's a 2x squared h, and 2xh times h, that's plus a 2xh squared. Now let's distribute our h squared to each term. And so h squared times x, that is plus xh squared. And then h squared times h, that's a plus h cubed. So there's some like terms in here. We have an x squared h plus a 2x squared h, that's a plus 3x squared h. I have a 2xh squared plus an xh squared. That is a 3xh squared plus h cubed. So I'm going to go and replace that in here. So we have 9, limit is h approaches 0. This whole x plus h quantity cubed, which was x cubed plus 3x squared h plus 3x h squared plus h cubed. Then I have this minus this x cubed all over h times the square root of x plus h quantity cubed plus the square root of x cubed. Notice our x cubes cancel. If our x cubes go away, then every term in our numerator now has this factor of h in common. And we can pull out a single h, and that will cancel with the h in the denominator. So if we did that, we have 9 times the limit. H goes to 0. So if I factored out an h, I'd be left with 3x squared plus 3xh plus h squared, and canceled it with the 1 in the denominator. I would be left with just that parentheses, the square root of x plus h cubed plus the square root of x cubed. So now when we go in and we plug in 0, wherever we see this h, we're going to be left with the 3x squared in the numerator. Well, the 3xh, that's 3x times 0, that goes away. And plus 0 squared, that goes away. So 3x squared is the only thing we have in that numerator. All over, well, this is going to give me the square root of x cubed, because that h is going to be 0. Plus the square root of x cubed. Those are like terms in the denominator. So 1 square root of x cubed plus 1 square root of x cubed, that's 2 square roots of x cubed. Well, remember our original problem back up here, that we had rational exponent. And so let's rewrite that square root of x cubed with a rational exponent, and then we can simplify that. And so if we do, we have in our numerator still 3x squared all over 2. Square root of x cubed, though, could be rewritten as x to the 3/2 power. And then using the rules of algebra of exponents, we have the same base in the numerator denominator. And so we can subtract the exponent. So we have 3 over 2. Whoops, and I need to go back because I noticed that I dropped my 9 here. I still have this 9 out here. Once I took that limit, I should still have this 9 out here. But 9 times that 3 in that numerator, that's going to give me 27 there. Okay, so going back to what I was saying, if we look at rules of exponents, we're going to take the one on top, 2 minus the exponent on the bottom, 3/2. Common denominator, it's really 4/2 minus 3/2. And so this is going to give me x to the 1/2. So dy dx, the derivative of y with respect to x is 27 x to the 1/2 power all over 2. Okay, so recall that the derivative, and we're just looking at the derivative of a function, f of x, with respect to the variable x, is the function f prime, whose value at x is given the following. So the derivative of f of x, which we could write as f prime of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that the limit exists. So an alternative form is to look instead, setting up the derivative of f of x to equal the limit as z approaches x of f of z minus f of x all over z minus x. Okay, so we are looking at this as z is equal to x plus h. Notice if we plugged back this in, wherever we saw z, we would have the same formula up here. So I would have f of c is z here. I'd have x plus h minus f of x. I see a z here, plug in x plus h. Then I have this minus x. And so notice that down in my denominator, I have x minus x, and those cancel out. So that leaves me with what I had over here. And z is approaching x. And the reason why that is because h is approaching 0. If h is approaching 0 down here, then z is going to be approaching x. And so this is an alternative form of using the definition of a derivative to find the derivative of a function. So let's look at that one example doing that. But like I said, it's up to you. You can do the method that you prefer. I tend to prefer the one above. Okay, so we're looking at this example of using that alternative form. And we're given that the alternative form, which I had just said above, f prime of x is equal to the limit as z approaches x of f of z minus f of x all over z minus x. We're going to use this form to find the derivative when f of x is equal to 1 over x plus 2. So let's look at what it means for this piece, f of z. So we're going to say f prime of x is equal to the limit as z approaches x Well, when it tells me to find f of z, it's just telling me to go into my function f of x, right? And wherever I see an x, I'm replacing it with z. And so doing that, I'm going to have 1 all over z plus 2. And then it tells me to subtract off, so minus my function of f of x. So minus 1 over x plus 2 all over z minus x. So z minus x. But notice if we go in here and we plug in x wherever we see a z, in the numerator, I'm going to have 1 over x plus 2 minus 1 over x plus 2, which is 0. And in the denominator, I would have x minus x, which is 0. So I have that indeterminate form. And so I have to manipulate it to get rid of that form so I can get the derivative function. Well, if you're dealing with a complex fraction, let's get rid of that complex fraction. And one way is to multiply by the least common denominator of the numerator. I'm sorry, least common denominator of all the fractions within. And so in this case, we have z plus 2 and x plus 2. So if we distribute that to the first term, let's bring down our limit. So we have the limit as z approaches x. Distributing it for the first fraction, the z plus 2 cancels, and you're left with just the x plus 2. Minus, I need parentheses. And when I distribute this to the second fraction in the numerator, the x plus 2's cancel. So I'm left with a factor of z plus 2. All over, I'm going to leave it in this form, z minus x, all times z plus 2 and x plus 2. So once we distribute that negative, we'll get the following. We'll have x plus 2 minus z minus 2 all over z minus x z plus 2 and x plus 2. So notice I have a positive 2 and a negative 2 down in that numerator. I'm sorry, yeah, in the numerator. If I look at this, I got the limit then as z approaches x of x minus z all over z minus x, z plus 2, and x plus 2. I'm still, if I go in there and plug in x wherever I see a z, I'm plugging in x wherever we see a z. I notice my numerator, I'm going to have x minus x, which is 0. And then down here in that denominator, I'm going to have x minus x, which is 0 times some other things. So that's still 0. So notice that our factors are almost identical in the numerator denominator. We have an x minus z in the numerator, and we have a z minus x in the denominator. So we're off by a factor of -1. And so we can pull out a -1 from one of those and rewrite it. So if we pull out a -1 from the numerator, that would be -1 times, I'm going to rewrite the order, z minus x, or we put negative x plus z. all over that z minus x, z plus 2, and x plus 2. So now I can cancel the z minus x's. And now when I plug in, go back in to plug in, I notice that it's gonna not give me that indeterminate form anymore. So I have -1 in my numerator all over z plus 2, x plus 2. So wherever we see a z, we're replacing that z value with x. So that's -1 all over x plus 2 times x plus 2. Or x plus 2 quantity squared in that denominator. So -1 all over x plus 2 quantity squared. This is the derivative of our f of x value. If f of x is 1 over x plus 2.
Professor, how do we pull out that negative in front of on the third step?
Yeah, right here. So we needed to pull that -1 out because we have this factor, let's just think of this x minus z on top, and we have this factor on the bottom, one of them, that was z minus x. So notice that in the top, it's +1 in front of my x and -1 in front of my z, where it's opposite signs in the denominator. I have a +1 in front of z and a -1 in front of x. So if we pull out -1 from the top, that would make this x negative x, because -1 times negative x gives me the positive x on top. And that would be plus z, because -1 times this z gives me the negative z. And so I just rewrote this, and it's all over z minus x, as -1 times z minus x. Just switching the order, because we can, as long as we carry the sign, adding two things, it doesn't matter the order that we're adding them in. And so now you can see more easily that these are like factors and they cancel. Does that help?
Yeah.
Okay, awesome. Other questions on that? Okay, so we are now going to jump in and we're going to look at graphs of a function and try to look at and graph the derivative function. I think that's what's next. Let's see.
Really quick, Ms. Nothinger, about this problem. Do you have to use that equation right there, the z to x, or can you use h to 0 too?
So I'm okay with you going ahead and just using the limit as h goes to 0 of that difference quotient like we have been. And that's how you're going to be seeing me do it, unless it was a question then in the textbook that asked me to. You guys were asking me to do that, but I'm okay with you guys just doing it the way we've been doing it all along.
All right, sounds good.
Okay, so graphing the derivative. So we can make an appropriate, let me just read this off, sorry. We can make an approximate plot of the derivative y equals f of x by estimating the slopes of the graph of f. That is, we plot the points x, f prime of x, in the xy plane and connect them with a smooth curve, which represents y equals f prime of x. So I want to go down. There were some interactive features I wanted to show you, but let's first look at an example. Before I do that, I just again want to restate, because it was just restated a little differently, but the same thing I just said, relationship between the graphs of f and f prime. Since a derivative at any point is equivalent to the slope of a function at that point, we can graph the derivative given the function by estimating the original function, what it looks like when you're given the graph of the derivative. Okay, so let's say you're given the following graph. And that's the graph of f of x. So when you're doing the homework, just make sure you look to see, are they giving you the graph of the original function, or are they giving you the graph of the derivative function? And so this one is given the graph of f of x. We want to sketch the graph of the derivative function at the same set of axes. So this one isn't too bad, because notice that there's different segments, but each segment of the graph is a line. And so if we look at this segment of our graph right here, all we need to do is we need to figure out what the slope is. And we know we can figure out the slope of a line. And so you could actually do it pretty easily without even choosing 2 points, right? If I rise one here, I'm running one here. So rising,
Rise over,
yeah. So
rise over run.
Right. And so rising one is 1, but we're running 1 to the left. So that's going to be -1. So we know that the slope, any point that you choose on this, when I chose green, that it's going to have a slope of -1. So on f prime of x, we got some points here. So I know that when x is -6, f prime of -6 is equal to -1. Because that's the slope at that value. At x equals -5, if I plugged in that value into my derivative function, that slope at -5 is still -1. That's all the way down till I get to this point here at -3. So at -3, I still have a derivative of -1. So for that section of my graph, if I'm graphing my derivative function, I'm having a horizontal line. That's a horizontal line at -1. I'm going to move this so we can see the horizontal line. So I have a horizontal line until I reach this value. I'm going to leave an open circle there for now, and we'll talk about that more in a minute. And that brings up a great point. So now let's look at that next piece of our graph. So again, this is a line. And so if I look at this line, I can figure out what the slope is for that piece. So looking here, again, rise over run. If I rise up 3, I'm running over 2, so -2. So now for these x values, so if I chose the x value here of, let's say, -2, if I plug that into my derivative function, the slope there at -2 for my function is, we found to be -3/2. And that's going to happen all the way until we get to x equals 1. So x equals 1, we also have prime of 1 equals -3/2. Okay, so -3/2, that's going to be about here. That was here. Oops. And I'm going to go until I hit x equals -3. And I'm going to have an open circle there. So what do we know about a slope of a horizontal line? It's not rising any, it's just running. So we know that the slope is 0. And so at this point, I'm going to have an open circle. And I'm going to have a horizontal line at 0 until I get to 3. And then the last piece of the graph, again, I have a line, so I want to figure out what that slope is. And so if I look at that slope, again, rise over run, let's see, looks like I'm rising up 2 and running over 1. So my slope in that case is 3/2. And so I'm going to have a horizontal line because any value from x equals 3 to 6, I have 3/2 as my slope. So I'm going to put an open circle here and then 3/2, which is 1.5 to here.
Wait, won't the slope be 2?
Did I get that wrong? Was it rise 2, run over 2? Yes, rise. Yes, you're right. Rise 2. What did I just say? Okay, you're right. Thank you. So rise 2 and over 1. So that changes. Thank you. So we get a graph that looks like this. So these are all graphed on the same axes. And I was trying to represent each piece of the original function f of x in different colors. So you can see that that was the same slope. And so in this case, we have different kind of steps in here. Notice that our derivative, notice that where our graph was decreasing. So notice that in here, it's decreasing. Our slope is negative, right? When it's decreasing. And notice that for our function, this is all below the x-axis for our derivative function. Here, our slope was 0 because it was horizontal. Notice that's on the x-axis. This piece here, we're increasing. And notice that the derivative function of an increasing function has to fall above the x-axis. And so that's kind of important information that you'll be using to help you graph these. So I kind of wanted you to notice again that our graph of our derivative function, they had kind of steps and they are undefined. I had made it undefined at certain values. Oops, this should have been an open circle. And so let's look at what it means for a function not to have a derivative. So when does a function not have a derivative at a point? So a function has a derivative at a point x of 0 if the slope of the secant line through that point p x of 0 and f of x of 0 and a nearby point q on the graph approach a finite limit as q approaches p. Okay. So thus differentiability is smoothness condition on the graph of f. A function can fail to have a derivative at a point for many different reasons, including the existence of a point where the graph has, oops, the following. Okay, so a sharp corner. So in this case, we have a sharp corner. And so depending on where we choose our point to look at that average rate of change, so if we chose the point here, then we would get a slope that looks like this. So it just depends on where we choose the point. If we chose some point here, you know, the more we go over, the more it's going to be in that direction. But let's say we chose a point over here, and then NP, and look the secant line, we have a different direction. Our slope is different depending on which side that we're coming in on to that point. And since the derivative or the slope is not the same, then it doesn't have, it's not differentiable at that value. So another way that it wouldn't exist if you have some sort of a cusp. So a cusp where the slope of P and Q approaches infinity from one side and negative infinity on the other side. This example 3 is where we have a vertical tangent line, where the slope of P and Q approach infinity both sides, or negative infinity from both sides. If you have a jump, so notice there's a jump in here, it's kind of maybe harder to see. There's a jump in this graph, and so if there's discontinuity, then it's not going to have a derivative. But here's also a case where there's a discontinuity. So a function has to exist there, and it does, but the derivative at this point is vertical, where it depends on where you're going. And the last case where the derivative doesn't exist is if you have a wild oscillation, which we had seen in this graph of x times 1 over x. As x approaches 0. So the last example shows that a function is continuous at x equals 0, but those graph oscillate widely up and down as it approaches x equals 0. The slope of the secant line through 0 oscillates between -1 and 1 as x approaches 0 and does not have a limit at x equals 0. Okay, so those are cases where a function would not have a derivative. And that's what's happening graphically. We're going to stop there. We are still not done with this section, but we're almost done with this section.